continue our work on section 4.3 in our book, and we're going to keep working on factoring. Now, just a refresher, factoring is when we take an equation like this and we put it in factored form, where we have our x and we have our two intercepts as each piece in parentheses. They're also set to 0, just like in our standard form. Now, the reason why we can factor and why it works is because of what we call the zero product rule. And what this means is that we can take two things, we'll just call them A and B. If they're equal to 0, that means this piece, A, could equal 0, and B could also equal 0. Which means, and I'm just explaining the property, this isn't a big deal, but what this means is that this piece here could be like A, and this piece here could be like B. So really, if we applied this rule to this example, we would say that x minus 5 could equal 0, and that x minus 1 could also equal 0. So we would solve for x. We would get x equals 5 and x equals 1. And again, yesterday we talked about how if we take our solutions, our x-intercepts to our quadratics, we can write them in factored form using x minus q and x minus p, where q and p are our two intercepts. Okay? So again, this just kind of proves to you how this works. This is called the zero product rule. So today we're going to focus on 3 types of factoring. The first one is called using the greatest common factor. Now, this type of factoring can only be used when you have a binomial. A binomial, here's an example and here's another example, is when you only have 2 pieces to your equation. Okay, bi, we know from our roots that that means 2, so it implies that we are going to have 2 pieces. Now, greatest common factor, we've used things greatest common this, least common that, and in the past, what we're going to do is we're going to see what can we pull out of each of our pieces of our binomial to simplify the inside down. So this one piece inside looks like a set of parentheses and is almost in our factored form there. So if we look at these, the first thing we're going to do is we're going to look at our coefficients. Okay, here 16 and 8. Clearly I can think through this in my head and realize I can pull 8, that's my greatest common factor, out of both of these pieces. So if I pull an 8 on the outside, okay, so I'm kind of doing the opposite of distributive property, this becomes 2x squared, because that would have given us 16, and this becomes just a plus x if I divided each piece by 8. 16 divided by 8 is 2, 8 divided by 8 is 1, we keep our x. So right now that might seem like it's factored all the way. Okay, and you know what? Our coefficients are factored all the way. We can't do anything with the numbers in front. However, the second thing you need to look at is if you can factor out an x. Now here, x squared means x times x. And here, this is just like 1x. So we could take an x from here and an x from here and pull that outside also. Now we don't pull out an x squared, we're just going to pull an x out from this and an x out from that. So outside we'll have the 8 from 4. An x, and then here we still have the 2. If I take this x out, we're only left with x, so it's going to be 2x. Plus, if I take this x out, or divide by x over x, it's not 0, folks, it's going to be just 1. And this right here would be our factored equation using the greatest common factor. Now we can solve this, okay? This piece here, if we think back to our zero product rule, each of these pieces could be set equal to 0. So this piece could be 8x equals 0, and this piece could be 2x plus 1 equals 0. When we solve each of these are going to be our 2 solutions. So to get x alone, divide by 8, I get x equals 0 over 8, which is just 0. That's one of my solutions. And now my other solution, I'm just going to isolate my variable. So I'm going to subtract 1. I have 2x equals negative 1. And then divide by 2, x equals negative 1/2. Okay? So these 2 are my solutions. So if the directions were factor this and find our solutions, I don't have to make a graph anymore. I can pull out my greatest common factors, set each piece equal to 0, and then solve to get these numbers. I no longer have to graph them into a table. Let's try another example. And with this one, we'll finish up our steps. So initially, we see this. It's a binomial. It has two parts, so that should trigger in your head, okay, I'm going to use greatest common factor. Greatest common factor always happens with the two-part things, okay, our binomials. So looking here and here, I'm looking at my coefficients. I can see from each of these, I can pull out a 4, okay? If I pull out a 4 from this piece, divide by 4, I get y squared. Here, if I divide by 4, I'm left with a positive 4y. Now, I'm going to see, can I factor out an x? Now, clearly here we don't have an x. Okay, that just means can we factor out our variable? And we can factor out a y. So I'm going to take a y and pull it out here. So I'll have a 4y. I'm going to divide by y, okay, kind of like what we did here. Y squared, which is just y times y, we have those cancel, and we're left with one y up top, so y. Here, y divided by y, that cancels, and we're left with just 4, so this becomes y plus 4. This here is in factored form, but we need to get our solutions, our x-intercepts, where it hits those axes. So I'm going to set each piece equal to 0. For y equals 0, and y plus 4 equals 0. Divide by 4, divide by 4. I get y equals 0. And here I'm going to subtract 4. I get y equals negative 4. These are the two solutions to this equation. So after I've checked my coefficients, I've factored out a letter if possible, I'm going to set each piece equal to 0. And my last step obviously is going to be solve. Now, one thing that will, generally speaking, happen is you're going to have one variable that's always going to be equivalent to 0. If you have something popped outside here and there's no addition or subtraction, that solution is always going to be 0. So this isn't just an uncommon pattern. The fact that one of the variables is 0 is going to be something you're going to come across every single time that you can pull a letter on the outside. If there's a letter on the outside, there will be one value that's going to have a 0. The next type of factoring that I want to talk about has to do with perfect squares. Now these are always going to be trinomials, which means that it's going to have 3 pieces to it. Okay, it's going to have its ax squared plus your bx plus your c, a trinomial. Now, this will not always be able to be used. Just like the last strategy we did, you have to have our binomial with the x squared and the x. Here, perfect squares will only work if your actual quadratic is going to be a perfect square. So first things first, you're going to want to check if your actual equation is a perfect square. Okay? And the way that you do this is by looking at your C value and your B value and hoping that your A is just 1. So here, your C value must be a perfect square. Okay? So it could be the result of any number being multiplied by itself. So 4 is a perfect square, 25 is a perfect square, 100 is a perfect square. Anything that has a nice whole number as its square root. So 64, clearly that's a perfect square because 8 squared, or 8 times 8, is going to be 64. So I'm thinking that this is yes for step 1. It's 8 times 8, and that's going to give us our 64. So far we're in the green. All right, that does not mean you have a perfect square yet. All it means is now we have to go to our second step, which is to look at your b. Our b here is 16. That is going to work. Your b must equal 2 times whatever your number was that you got here. Okay, so if we look, we said the square root of 64 is 8, so that works. We're going to take that 8, we're going to double it. That's 16, that means this works also. If both of these things pass, then you know that you have a perfect square and you're going to be able to factor it quicker using our perfect squares rule for factoring. Okay? So I just summarized those steps over here so that you could write those down. The 2 things you want to look for is to check C. Is it a perfect square? If your answer is yes, you're going to check B. is, you're going to find the square root of c, multiply it by 2, and then if that is equal to b, then you're good to go. Again, all of these would have to be positive, okay? You could have this being a negative 16, because negative 8 times negative 8 does equal 64. So negative times 2 could be a minus 16. However, here, because it's positive and this is positive, we know we're dealing with a positive 8. Okay? So this is what's awesome. Perfect squares, if it passes both of those, factoring it is really easy because it's always going to follow the same step. You're going to have your x as your first value. You are going to have whatever your square root of c is. Now we know it could be plus 8. We know it could be minus 8. However, when we multiply this by 2, we get positive 16. Here, when we multiply it by 2, we get negative 16. We had a positive, so we know that positive 8 is going to be our square root of c this time. So we're going to take that positive 8. We are going to add it to our x. And then we're actually going to square that. And that would be our factored form. Now when we square that, we're just saying take this and multiply it by itself. So really it's the same thing as x plus 8 times x plus 8. If you like it better this way, write it this way. Okay, it's the same thing just twice. It's kind of like when we had one solution. Okay, here, this is the equivalent thing, but you need to know, because on an assessment you may see the squared outside of here. You don't distribute that square. You actually take this whole chunk and multiply it by the other, which just puts us in factored form. So once we have this, we're just going to go through and solve it. Okay, again, we're going to use our zero product rule. So we're going to have x plus 8, this piece. We're going to set it equal to 0. Here we're going to have x plus 8. We're going to set it equal to 0. So we see in this instance that each time we get negative 8 as our answer. It doesn't hit negative 8 twice on its graph, okay? It only hits x once, and the one time it hits it is at negative 8. So here, we're going to get a result that is going to be one solution. Most perfect squares, in fact, all perfect squares, are going to only have one solution. And when you solve it twice like this, you should get the same number each time, okay?